DGX A100 is not just a super fast hardware server, but actually a huge value of it comes from its software. That is why we say it's a complete AI appliance, not just a server or a meta server. As you can see in this slide, the DGX A100 comes with a complete software stack. And this stack enables the system to be very fast and to process large volumes of data. So it also makes data scientists able to start their work from day one. The typical work of a data scientist on a typical deep learning server is to first install the operating system. And then on top of that, the data scientist needs to install the correct and up-to-date GPU driver, then the correct CUDA version. A lot of work is done here to install and solve compatibility issues for the GPU. After that, a container platform and an AI framework needs to be installed. And again, the framework version should be supported by the installed CUDA and the programming language. Think about it. It's a problem for data scientists because now you have the GPU driver and the CUDA developed from NVIDIA. And you have the container platform like Docker, then you have the programming language developed by the community, and the frameworks developed by, for example, by Facebook. Each one of those software components is developed by different entity, and the new releases come out at different rates. New versions are not necessarily tested with all other components, and it's very common to have errors because of non-compatibility of those components. So ensuring that everything works correctly with every other thing whenever a new component is updated is very time consuming. I can tell you as a data scientist that this is a pain that I should experience regularly to do my job. This is called the do-it-yourself approach. Now on the DGX, all of this is taken care of by NVIDIA. How is that? NVIDIA optimizes each software component monthly and when a new version comes out. So the team ensures that everything works together whenever a new package comes out or a package is updated. So the data scientist or the system admin can update the whole software stack with 1 or 2 commands, and that's it. So as you can see on the right, the software stack on the DGX starts with a customized version of the operating system. On top of that is the GPU driver and the container platform, and then comes the artificial intelligence framework. Everything is tested, everything works smoothly, and everything is updated and ready to use with 1 or 2 commands. Now, when you are installing the DGX for a customer or proposing it, the customer will ask you questions about these software components, like if you will install CUDA and TensorFlow, for example, as part of your implementation. Because again, this is a hassle. So I will walk you briefly through these components so you have a good understanding to carry out that conversation. The first and one of the most important components is CUDA. CUDA is one of the things that come ready for the DGX. It's basically a platform that developers and data scientists use to program the GPUs, i.e., the GPU on the system cannot be used to run programs and codes without having CUDA installed. It's not a new programming language itself, but a toolkit that can be used by many common programming languages, as you can see here. Like for example, C or C++ or Python or Java, among others. As said before, a new version of CUDA comes out frequently. and not every version is supported for every GPU. For AI, every framework and application is using CUDA, as you can see on the left. Not only AI, but also HPC or high performance computing. Every application is using CUDA to run on GPUs and provide faster results or fast simulations. So, how do developers or data scientists use CUDA? They write their program codes as usual, which run on CPU. Inside the program, there is a part that is computationally intensive and will need to run on thousands of cores. They need to run on thousands of cores to have the results computed in the required time. So the developers specify that part that will run on the GPU and how it should run. So overall, as you can see here, the codes run sequentially on the CPU as usual. It's a serial code, and when the part that will run in parallel is reached, the GPU cores take care of it. And after it finishes, the CPU comes back into action. Okay, let's take an example. Let's say a government agency wants to take photos of some architectural lands by drones, and they want to analyze them to determine the type of plants planted there, or to see if some illegal plants exist in that area. So the program or the AI code should take the photo as an input and does some processing on the photo to know the type of the plant. For example, the program will detect these white edges of the leaves here, as you can see. Or it might also search and process the color in the center of the plant to determine which type is it. These processes or these calculations are extensive. So developers decide that this part, the part of processing or searching for the edges and the colors, will happen on the GPU to have fast results. So first, they partition the input or the photo to be processed by the 7,000 cores on the A100 GPU. You see here, for example, it's partitioned to 3 parts, part 1, 2, and 3. And then these parts are copied to the GPU for processing. Now, after the image is partitioned and loaded to the GPU, the program or the parallel code that will run on that image should be loaded also to the GPU to start the processing. Now, after the codes are loaded to the GPU and the processing is carried out, the GPU has finished the work and the results are already calculated. Then they send these results back to the CPU to visualize it or to display it to the customer or the user and or take some further actions. All of this is done using CUDA. So CUDA is responsible for partitioning it, for sending it to the GPU, loading the codes, running them, and then gathering the results and sending them back to the CPU. This was a very high-level overview. You will not need to do anything with CUDA yourself because, again, it has been taken care of by NVIDIA. Any questions? The next part or component is Docker, which is the containers platform. But before talking about Docker itself, let's first define what are the containers, why do we need them, and how they make things different. On the level of the definition, containers are a form of operating system virtualization. The container is a standard software unit that packages up or encapsulates the executables, binary codes, libraries, and configuration files and all dependencies in one unit. So the application can run quickly regardless of the computing environment, because everything is included together in a package. A single container might be used to run anything from a small microservice or software process to a large application. Containers provide the environment for building, testing, and deploying the software, allowing reproducible builds, execution environment rolled into one, and simplifies application deployment. Now we know what are containers generally, so let's talk about Docker. Docker is a platform that delivers these containers, and Docker containers run on Docker engine using Docker engine. And this Docker engine acts as a client-server application with the following. There is a server with a long-running daemon process called Dockerd for daemon, APIs which specify the interfaces that the programs can use to talk and instruct this Docker daemon or the server, and a command line interface client. The containers that run on Docker engine are standardized because Docker created the industry standard for containers, so they could be portable anywhere. They are also lightweight because containers share the machine's operating system kernel, and therefore they do not require an operating system for each container or for each application, unlike virtual machines. And this drives higher server efficiencies and reduces the server and licensing costs. And lastly, containers are secure. Applications are safe in containers, and Docker provides the strongest default isolation capabilities in the industry. Sometimes there is a confusion between containers and virtual machines because both of them are some sorts of virtualization. So virtual machines are abstraction of the physical hardware, turning one server into many machines. The hypervisor or the software that creates and monitors those virtual machines allows multiple machines to run on a single server. And each of those virtual machines includes a full copy of the operating system and the necessary libraries, which takes tens of gigabytes. On the other hand, multiple containers can share the same operating system. So each container does not need to have a full copy of the operating system within. And each container runs in an isolated process. That's why containers take less space than virtual machines, and they can be used to run multiple applications concurrently. Now, when we talk about Docker, we always use the terms Docker images and Docker containers. So what are the differences between them? Starting with the Docker image, it is the basis of Docker containers. It contains layered file systems stacked on top of each other, and it has execution parameters to be used within the container runtime. And finally, Docker image does not have a state and never changes. On the other hand, the containers are the runtime instance of the image. So when you launch an image or run it, it becomes a container, or a container is launched. It has a state and it changes, and each container has three things: the base Docker image that it was launched from, the execution environment, and the standard set of instructions. As said before, Docker uses a client-server architecture. The Docker client talks to the Docker daemon, which does the heavy lifting of building, running, and distributing the Docker containers. The Docker client and daemon can run on the same system, or you can connect a Docker client to a remote Docker daemon on another server. The Docker client and daemon communicate using REST API over Unix sockets. The Docker daemon listens for Docker API requests and manages the Docker objects such as images and containers and networks and volumes. A daemon can also communicate with other daemons to manage Docker services. The Docker client is the primary way that many Docker users interact with Docker. When you use commands such as docker run or images, the client sends these commands to the daemon, which carries them out. Docker registries store the Docker images that you have. Docker Hub is a public registry that anyone can use to store his images and download them. And Docker is configured to look for images by default on the Docker Hub. You can even run your own private registry and configure Docker to search for the images you want on your private registry. Docker objects include images, containers, networks, volumes, and every other object that we mentioned previously. Docker does not natively support NVIDIA GPUs within containers. But since containers can have great effect on the deployment of AI applications that use GPUs, NVIDIA created NVIDIA Docker to support the development and deployment of GPU accelerated containers. NVIDIA Docker provides the two critical components that are needed for containers to access the GPUs. The first one is driver agnostic CUDA images, and these are images of CUDA that does not depend on the installed GPU driver. And the second thing is a Docker command line wrapper for NVIDIA that enables GPU to be accessed by the container at launch. So now we have a good knowledge about the containers, the platform, and NVIDIA Docker. So let's see some basic commands that you need to know, and later on you will see in a lab how to use them to download an AI framework and launch it. First, we can start by checking the current Docker version through this command, docker version. We will get all the information about the currently installed version and also information about the client and the server. We can also get all the details on the current server through this command, docker info. It gives all the information about the number of images that you have, the number of containers, the number of running, paused, or stopped containers. Also, it gives information about the operating system, the system architecture, the total memory used, the CPUs and the GPUs, and also the registry on the system. Once we checked the Docker version and assured it's working properly, we can check all the current Docker images that we have on the server with the command docker images. Different parameters can be passed to display different options. If we use Docker images without any parameter, this will be the results as shown here. It will display the repository of the image and the image name, the image tag, and the image ID, the date it was created, and the size of that image. Docker images have intermediate layers that increase its reusability, decrease the disk usage, and speeds up the Docker build. These intermediate layers are not shown by default when you use that command. The size is the cumulative space taken up by the image and all its parent images or layers. This is also the disk space used by the contents of the tar file created when you do Docker save an image. An image will be listed more than once if it has multiple repository names or tags. This single image, identifiable by its matching image ID, uses up the size listed only once. Next is the time to check NVIDIA Docker as well. First, we check the current NVIDIA Docker, and the output will display the current version, same as we did for Docker. If needed, we can upgrade the current version, but before doing this, we should stop the commit and remove the containers you want to save. Then we can upgrade the current versions through apt command. First, we do apt update. Then we download the latest NVIDIA Docker package, then installing the downloaded version. Once you have the latest Docker and NVIDIA Docker, let's use them to run a container that uses GPU. To run a container, we use docker run command. And there are two ways to utilize the NVIDIA Docker wrapper. The first is to specify the runtime to NVIDIA, and the second is using NVIDIA-docker run. And note that passing GPUs all parameter assumes that the system has NVIDIA Docker installed and used. Here we can see running docker run to run container called cafe from NVIDIA NVCR repository. These are the most common commands for managing Docker images. Docker images command, as we've seen, docker rm command that's used to remove specific image with its ID, delete it, and we can pass different parameters to the same command to remove all images if needed. To list all active running containers, we use this command docker bs, docker stop to stop a specific container that's currently running, and docker rm to remove the Docker container as we said. To install or download more Docker images, we use the command docker pull. And there are 4 options to pull a Docker image or container. First, from Docker Hub itself. Second, from NVIDIA DGX repository or NVIDIA NGC. The third is from a local repository that's on the system itself. And the fourth way or method is to do it from a specific file. Now the final topic in this section is the NVIDIA registry for the DGX users. What is it? DGX users have private registry service, and this registry includes an updated set of Docker containers for the frameworks monthly, included in the container source code, and these are open source frameworks, scripts for building the frameworks, Docker files for creating containers based on these containers, markdown files that contain text about specific containers, and tools and scripts for pulling down datasets that can be used for testing or training AI applications. Users get access to this registry after registration from NVIDIA support. Then they can use these credentials either through the Docker command line or through the NGC, which is NVIDIA GPU Cloud, and we will discuss about NGC in the next section. If you have any questions regarding Docker or NVIDIA Docker or containers, please ask. Next, in the software stack comes the NGC or NVIDIA GPU Cloud. And if you remember in the first slide, when we talked about the software stack, first we started with the operating system, on top of that with the GPU driver, then the container platform, and on top of that comes the AI frameworks or AI applications. And NVIDIA GPU Cloud is the place that provides you with the containers for the AI frameworks and for AI applications that you are going to install for your customer. NVIDIA GPU Cloud or NGC is a cloud for AI and high-performance computing software. The NGC manages a catalog of fully integrated and optimized AI frameworks, and these frameworks exist as Docker images that take full advantage of NVIDIA GPUs in both single GPU and multiple GPUs configurations. These framework images are ready to run once you download them. Each framework image includes the framework source code, so the customer be able to modify and enhance the framework according to his needs. NVIDIA updates these frameworks monthly, to ensure that they continue to provide peak performance, as mentioned before. NGC is a resource for data scientists as it accelerates their work rapidly. Let's see a short video explaining it.
GPU computing is changing the world. It's transforming industries with the power of artificial intelligence. It's driving breakthroughs with high-performance computing. And it's delivering advanced tools that help users visualize and interact with massive data sets to find new insights. This revolution has created a new way to write software, where data is the new source code. It's fueled by new GPU technologies, community-driven and commercial software, and innovative thought leaders, including researchers, data scientists, and developers. Until now, leveraging this new way of working meant always searching for the latest frameworks and applications, getting the right drivers, and ensuring that your OS version and patches were compatible. NVIDIA solves these challenges with NVIDIA GPU Cloud, making it easy to access all the resources you need to do your best work faster. NGC brings GPU-accelerated software tools together in one convenient place, including NVIDIA-tuned, tested, and certified containers for all the top deep learning software, GPU-optimized HPC applications and visualization tools, and more at no charge. The containerized software gives you everything you need in a single, ready-to-run package. NVIDIA ensures that every container runs optimally on NVIDIA GPUs on the top public cloud providers, in the data center, and on the desktop. They deliver maximum performance by taking advantage of NVIDIA GPU innovations like Tensor Cores, NVLink, and NVSwitch. And the same containers run across all of these environments, providing a consistent hybrid cloud experience where you can easily move your GPU-accelerated prototypes and workloads across supported platforms. NGC increases productivity by eliminating all the time-consuming do-it-yourself work of creating and testing optimized software stacks, empowering you to innovate in minutes, not weeks, wherever your compute resources are located. This takes the complexity out of deploying GPU-accelerated software for your research and development, and frees you to change the world.
This is a slide that shows the importance of using the latest version from the framework on the NGC. Here we can see how the NGC updates makes difference in performance over time. So this is a benchmark on a model called Resident 50, and this is a very popular image classification model or AI architecture that's used for this benchmark. As a benchmark is done on 3 AI frameworks: MixNet, PyTorch, and TensorFlow. As you can see here, each update from NVIDIA or each release from NVIDIA for these frameworks presented a new performance or was faster than the previous version, as you can see here. Many AI applications have common needs: image classification, object detection, document classification, text-to-speech, sentiment analysis, and more use cases. When developing applications with these capabilities, it's much faster to start with a model that is pre-trained or pre-developed, and then data scientists can tune them for a specific use case. The NGC offers these pre-trained models for a variety of common AI tasks, and they are optimized for NVIDIA GPUs. These can be easily retrained by updating just a few layers, saving valuable time. Here we can see some popular pre-trained models in computer vision and speech or natural language processing areas, and how they can be used in retail, in healthcare, manufacturing, translation, speech recognition, and last but not least, recommendation. The NGC offers step-by-step instructions or guides to create deep learning models and provide sample performance and accuracy metrics for data scientists to compare the results to. These scripts provide expert guidance on building AI models for image classification, language translation, and speech, and more. Data scientists can quickly build performance-optimized models by easily adjusting the models or the hypermodels of them. In the NGC, there are also two things called collections and Helm charts. Collections provide detailed documentation to deploy all the content needed for a specific use case, like object detection, for example. Helm charts automate software deployment using Kubernetes, which allows the users to focus on using the software rather than focusing on installing it. NGC private registry allows DevOps teams to push and share their Helm charts, so teams can take advantage of consistent, secure, and reliable environment to speed up the development to production cycle. Now let's see how to use the NGC on the DGX. So when we talked about Docker, we mentioned that DGX users or customers have access to something called the private registry. Let's explain now how they can access and use it through the NGC. After purchasing a support entitlement with NVIDIA, the end customer will receive an NVIDIA entitlement certificate via email. The email will include all the pertinent instructions needed to register for technical support. Here is an example of the NVIDIA entitlement certificate email that the customer will receive. The entitlement certificate itself is provided as a PDF attachment, and the PDF also includes instructions for using the certificate. If you already have an account, you can log into the NVIDIA Enterprise Support portal right away. If you are a new user without an NGC support account, click NVIDIA Enterprise Support Registration Form link. This link will have embedded information regarding your account. It's very important not to share this entitlement link outside of your organization. Registration will provide an NGC private registry account in addition to the NVIDIA Enterprise Support account. You will receive a welcome email, at which time you can activate or create your NGC private registry account. After the NGC private registry account is activated, a new email will come that invites the customer or you to continue the login process. Follow the following steps to activate the account. Click on the link on the email, and click on the welcome guest icon from the upper right of the page. Enter your organization email, set the new password, click accept for the terms and conditions, and that's it. To access the containers that are logged for only DGX users in the NGC registry, you need to have an API key. To generate this key, follow these steps. Sign in to the NGC website. In the top right corner, click on user account icon and select setup. Click get API key to open the setup API key page. The API key is used to authenticate your access to the NGC logged containers. Click generate API key to generate your API key. Click confirm to generate the key, and then you will have it. Please note that you only need to generate an API key once. Now, once you finish with the registration, account creation, and the API key generation, it's time to use the NGC to pull or download the Docker image that you need. And there are two methods to do so. The first one is to pull the image from the NGC container registry using Docker CLI, or the second, pulling the image using the NGC web interface. We will go through each of them now. To pull a container through the Docker command line interface, you need first to log in to the NGC registry through the command docker login nvcr.io. Then you will be prompted to enter your username. Then you should enter the text auth token. This means that you will authenticate with the API key and not using the username and password. Then enter your saved API key. And once accepted, you are ready to pull your Docker images. Use Docker pull command then the registry name of the container that you want, and then the name of the image to pull it. So for example, here we use nvcr.io/nvidia and then the container name. The other method is using the web interface of the NGC. You can log in there, click registry in the left navigation, and browse to the image that you want. You will find a pull column. Click the icon to copy the docker pull command. Then you can open the command prompt and paste the command that you just copied and hit enter, and it will begin downloading for you. Now we have finished talking about the software stack on the DGX. You have a good knowledge about each component, and you know now how to install the required framework or any software that's needed on the DGX through the NGC and Docker. Next, I'll talk about a new feature introduced in A100 GPUs called multi-instance GPU. It's not part of the software stack, but it's important for you to know it, because it makes a lot of difference in the proposition of the DGX and the A100 GPU. An important feature was introduced for Tesla A100 GPUs, which are the new GPUs within the DGX A100 system. This feature is the ability of partitioning one single GPU up to 7 instances. And this is to reach full utilization and be able to run multiple workloads in parallel on the same GPU. Each one of those instances has its own compute resources, i.e. the streaming multiple processors. And also each one has its own GPU engines, like the encoding, decoding, and the copying engines. This feature is only supported in Coda 11, and again for A100 GPUs only. Now, before going into some details about this feature, what is the motivation or the benefits behind it? Why was it introduced in the new GPU? A common problem for data scientists and developers is that they don't fully utilize the GPUs that they have. For example, if a developer is training a model to identify the plant type that we talked about before, his code could take only 10 gigabytes out of the 40 gigabyte memory in the A100 GPU. So without partitioning the GPU, the entire device or the entire GPU will be allocated to that workload, and it's not fully utilized. Multi-instance GPU, or MIG for short, MIG's main motivation is to solve that problem by being able to slice the GPU into instances and run parallel workloads on each instance, so you achieve near 100% utilization. Now, some of you might know about virtual GPUs, or vGPU for short, which is used to give multiple users access to the same GPU. So how is MIG different from vGPU or GPU virtualization? Actually, there are lots of differences. I will highlight only the main ones in brief, and I will start with the difference in the basic idea of each of them. So vGPU works by temporal or time partitioning, i.e. a scheduler uses time slicing to impose limits on GPU processing cycles used by each user or by each virtual machine. So the GPU resources are actually shared between the virtual machines, and when the GPU utilization is high by one machine, the other virtual machines are affected and the virtualization performance decreases, because again, on a hardware level, the resources are shared temporally or in time. On the other hand, MIG makes up to 7 physically separated instances. So it's not a temporal or time partitioning, but it's a physical partitioning and separation. The resources are not shared, but partitioned between the users. So one instance could be 100% utilized, the other instance can still work with the same performance without getting affected with the utilization of the other instance. A note here that you should know is that you can use both for additional flexibility. You can combine virtual GPU with multi-instance GPUs. Another difference using MIG is that you can make heterogeneous instances. So for big workloads, you can have an instance that is 20 gigabyte in memory, for example. And for a small workload, you can have an instance with 5 gigabyte memory. Not only memory, but also the compute resources and the GPU engines can be done in or assigned to each instance this way. There are instance profiles that you can use to create the required instances. And overall, there are 18 combinations that you can create. The creation of instances is pretty simple, as you will see in the demonstration or in the lab. As an example here, the A100 GPU has 40 gigabyte memory, and in this example it's sliced to 3 non-equal instances with different workloads. There are some limitations when enabling MIG mode on the GPU. One limitation is that GPU to GPU communication is not possible anymore, whether it is through PCI Express or NVLink. As you can imagine, the goal of partitioning is to slice one GPU to small instances to run a workload on each instance. But if the customer's workload is so big that it needs like 50 gigabyte GPU memory to fit in, then the customer will have to combine two GPUs for the single workload. And the rest of the second GPU cannot be instanced and utilized for another workload. So if you enable MIG mode on GPUs, you cannot have a communication between two GPUs. Another thing is that this feature is available only for Linux operating system, whether it's through a bare metal process or a pass-through virtual machines. So for example, you cannot bus an instance to a Windows virtual machine or make instances on bare metal Windows servers. But on bare metal servers, the operating system should be Linux, and in virtual machines also the operating system should be Linux. And the last thing is that it's only available for Ampere architecture GPUs, as we said, which is Tesla A100 till now.
By default, MIG mode is not enabled on the NVIDIA A100. MIG mode can be enabled on a per GPU basis with the following command. If no GPU ID is specified, then MIG mode is applied to all the GPU on the system. Once enabled, you can list all the available GPU instance profile with this command. You can also list the possible placement available using the following command. The command shows that the user can create two instance type, 3G 20 gig, which is the profile ID 9, or 7 instance of 1 gig 5 GB, profile ID of 19. Let's create 7 instance of 1G.5 GB profile, which is profile ID 19 on this GPU. You can also list the instance. And now after creating the GPU instance, you can also create 7 compute instance with this command. Now you have 7 GPU instance to run 7 different workloads, either by same user or by 7 different users at the same time. It's very easy to create or delete these instances by using NVIDIA Driver API using NVIDIA SMI command. Let's delete these 7 instances and recreate the another set of unique GPU instance for our demo here. In this example, I'm going to create GPU instance with pool of 4 GPU. I'm going to use this instance to run training benchmark with TensorFlow. Apart from this 4 GPU instance pool, I also have 3 other GPU instances available to run other workload. So I will create 3 separate instances of 1 GPU each for these light inference workload. Let's create these 4 GPU profile on single A100. The profile ID for 4 GPU pool 4G.20GB is 5, and for 1 GPU each is 19. We can verify these GPU instance and then create respective compute instance using instance ID. If you run NVIDIA SMI command, you can see you have 4 GPUs with different resources to run your workload. Let's run TensorFlow training by pulling the latest container from NVIDIA NGC portal and run on 4 GPU profile. This user do not need full GPU to run this workload, as dataset size for training in this case is not that big. In the case of GPUs like V100, he had to dedicate one full physical GPU to run this training workload. But in this case, he's only using half of the GPU, compute and memory, and leaving other half for other applications and users. You can also watch the utilization of 1 GPU instance in NVIDIA SMI and can also check the other 3 GPUs instance are available for other users. Let's initiate a BERT Q&A inference application on NGC pre-trained model on one of the GPU instance. This is a very lightweight application and only requires a slice of GPU. In this case, we chose the lowest.
The last section in this enablement today is the industrial use cases that you can offer to your customers on top of the DGX. There are AI use cases in every sector that you can think of. In construction, smart cities, education, retail, healthcare, cybersecurity, government, agriculture. Every sector you can think of, we have AI use cases that you can offer in that sector. Starting with the most used currently AI-based medical imaging platforms. These platforms use pre-trained deep learning models on thousands of medical images to automate and standardize the process and increase scalability of the medical imaging. The models are trained to detect any abnormalities. They can be used for different departments like pathology and radiology. One of their most successful applications is lung cancer early detection and the initial screening for COVID-19 patients. AI can help in drug discovery also and in medical research. Deep learning is used to analyze huge amounts of data to extract information from genome sequential data that can help gain more insights and get accurate results and decrease the overall process time. Also, AI helps in clinical trial by identifying the right patients for the clinical trials. It improves trial documentation, summarizes the overall process. Immune system analysis through identifying number of white blood cells can be done using AI. In the automotive industry, we need for sure to start with object detection that help classify and localize each object in the image. Also, semantic segmentation to group all instances of the same class into one group for sake of scene understanding. Both of them are very important applications in the assistant driver applications and self-driving cars to give alerts for the driver in case of pedestrians crossing the road, for example, or give order to the system in case of self-driving cars, and also lane detection is very important in this area. On the level of traffic management, license plate recognition is being widely used now. Speed detection, near collision detection as well. Traffic analysis systems that capitalize on some of the mentioned applications to gather traffic data, make actions for traffic control, and for early response coordination. Other features also include the detection of model of the vehicle, the make of the vehicle, type of the vehicle, and the color. Security and surveillance is one of the areas where AI applications spread that fast due to the availability of CCTV cameras almost everywhere. There are a wide range of applications that can be important for border control, military, defense, security for public places, gated communities, enterprise buildings, and many others. Intrusion detection, for example, to identify the place and the person that is intruding. Abnormal behavior detection, where machines are trained on the normal behavior and it will give alerts for any abnormalities. This can help in identifying medical or security events requiring immediate response. Fire risks, irregular movement of people and vehicles. People tracking and re-identifications that can be used in authorized people authentication and watch lists prohibition. Objects tracking and re-identification as well. Threat detection, either on detecting specific objects like guns or detecting objects that are left behind and linking them with the owner. Moving to the retail industry, AI is used for predictive analysis. So you can make demand forecasting, warehouse optimization, logistics scheduling optimization, efficient risk analysis, and customer behavior analysis. You can also use AI for assortment optimization. So AI can consider past sales, the store size, the local trends, online behavior, and predicted weather patterns and more. All of that to determine which products would be the best fit for a given store location. It's also used for customer behavior analysis, as this includes people counting, generating circulation maps and heat maps, attention tracking, and sentiment analysis to know the impact of your user experience system on your customers. Now to the manufacturing sector. Robotics that use AI in its movement and scene understanding are widely used now in manufacturing. Predictive maintenance uses AI to early detect the breakdown time for machines. AI also detects defects on production lines, and 3D vision inspection undertake tasks that humans can sometimes struggle with. AI systems can build full 3D models for automatic inspection of the products. In agriculture, it's used for arbitrary planning. So AI-powered engines extract different plant types and characteristics just through placing them on the conveyor belt. It's also used for crop monitoring. So companies are leveraging computer vision and deep learning to process data captured by drones and/or software-based technology to monitor crop and soil health and do predictive analytics to track and predict various environmental impacts on crop yields, such as weather changes. It's also used for disease forecasting through identifying the patterns of defects in the plants and classifying healthy and unhealthy plants. In banking sector, RPA combined with AI is forming intelligent automation solutions, changing the way processes are done in banking sector, and covering a wide range of processes such as invoice processing. AI-based OCR is used for documents digitization. It enables banks to overcome a number of challenges caused by manual information extraction. It can read unstructured documents and extract information with high accuracy. In fraud detection, AI can be used to analyze large volumes of transactions to search and find fraud patterns, and then use those patterns to identify new frauds or to identify the fraud as it happens in real time. When fraud is suspected, AI models can be used to reject transactions in real time or flag the transactions for investigations. Also, AI is used for bank branch automation to provide some features like protection of bank personnel, surveillance of bank assets, protection of unauthorized areas, and do face recognition in the ATMs, as well as doing customer retention analysis.